This lecture is a continuation of the introduction to the seismic reflection method of prospecting. In the previous lecture we looked at how seismic energy travels through the Earth, the different kinds of wave motion that there are, and how the seismic energy is reflected from interfaces between different rocks in the Earth, and looked at the basic elements of the system we use to record those reflections and then display them so that they give us a picture of the rock structures in the Earth. Well, in this lecture we're going to look at the different kinds of reflection events that occur and how those appear on the recorded seismic traces. The main types of reflection events that we get are firstly primary reflections, then things called multiple reflections, reverberations, which are a particular kind of multiple reflection, and finally some types of events called ghosts. We'll look at these reflection events first and then at some of the other things that happen to them as the reflections travel through the Earth, and also look at the kinds of noise which are also appear on our seismic traces as they're recorded. Well, the first type of reflection event then is in fact the only reflection event that we really want to see. It's the so-called primary reflections, which is a series of ray paths in a model such as this, where energy is reflected once only from a particular reflector and back to a receiver. So we're imagining a situation where the Earth is made up of a series of rock layers of different velocity and density in each layer, so that between each of those layers there is a reflecting interface which gives a reflection of the seismic energy. So we're getting reflection travel paths from each of those interfaces, and since there's only one reflection on that travel path, it is called a primary reflection. Now, if we imagine that the seismic waveform that was traveling along each of these ray paths was like this, just a sudden sharp impulse of seismic energy, this is often referred to as a spike, then this is the type of trace we would record at a receiver here if we saw only these primary reflections. Now, we showed in the previous lecture that the reflection coefficient at an interface is determined by the differences in velocity and density between the two layers, and that reflection coefficient determines the amplitude of the reflected signal in relation to the amplitude of the signal which is incident on the reflection interface. So in this very simple situation then, our trace would show only the primary reflections, each of them being just a reflection of the waveform, which is a spike, and the amplitude of that spike would be proportional to the reflection coefficients at each interface. Where the reflection coefficient was negative, indicating a reversal in polarity of the seismic waveform, then we would see the reflection as a spike going in the opposite direction to the positive reflection coefficients. So the direction in which the impulse appears on the seismic trace indicates whether it's a positive or negative reflection coefficient, and the size of the spike is proportional to the magnitude of the reflection coefficient. Now, of course, the reflection coefficient depends on differences in velocity and density, so that if we know the size of the reflection coefficient, that tells us something about the differences in velocity and density between different rock layers in the Earth. And in fact, use of this is made in some of the more sophisticated seismic processes. But for the moment, then, we're only concerned with the fact that this is the type of trace we would obtain if we saw only the primary reflections, which are really the only ones we want to see, and if the waveform of the seismic energy was just a sharp impulse or a spike. Now, one of the other types of reflections which is very common on the seismic traces are what are called multiple reflections. And these are energy which travels from the source to the receiver by some kind of reflected ray path where there is more than one reflection along that ray path. So several examples are illustrated here. The energy is reflected first from this interface, traveling back towards the surface, but then is reflected, some of it is reflected down again from that interface, reflected back again from here, and finally reaches the receiver. Now, of course, at each one of these interfaces, some energy is reflected and some is transmitted. So we're really only just looking at one particular ray path out of a very large number. This is one which is multiply reflected before it arrives back at the receiver. We have another example here where the reflections take place between 3 different interfaces, and another one here where there are even more reflections at several different interfaces. Now, if we looked at the seismic trace that we might record at the surface from an Earth situation like this with several layers, where we saw both the primary and the multiple reflections, that trace might look like this. The primary reflections are indicated by the little dot above them, and then all the other events that appear on here are multiple reflections. Now, you'll notice that in general those multiple reflections have a smaller amplitude than the primaries. And this is because each time the energy is reflected from an interface, its amplitude decreases to some extent, to quite a large extent in fact. So that the more times the energy is reflected, the more its amplitude decreases. And so in general, the multiple reflection amplitude is lower than the primary reflection amplitude, although it can still be relatively strong in some situations. This means that the multiple reflections are maybe not as bad as might seem at first on the seismic trace. Another factor which decreases their significance somewhat is that, of course, every time the energy is reflected backwards and forwards between the rock layers, it increases its travel time, so that the multiples, of course, always arrive at later times than the primary reflections from any of the interfaces involved, and therefore may, in fact, occur after the recording has ceased. So, of course, there wouldn't be any trouble to us in that situation. Now, one particular characteristic of a sequence of multiple reflections is illustrated here. If we just look at 2 particular interfaces in the Earth, we would have primary reflection travel paths from those interfaces, and we would also have a series of multiples which are generated by energy which bounces up and down in that particular layer. so that you would have a series of travel paths of increasing travel time, such as this, giving a sequence of reflections, such as this. We'd see the two primary reflections, then they would be followed by a sequence of multiple reflections, M1, M2, M3, indicating the number of times the energy is bounced up and down in those layers, and with the amplitude decreasing at each stage, because each time a reflection occurs the amplitude decreases. Now, an important property of a sequence of multiples such as this, all generated in the same layer, is that they occur at regular time intervals following the second of the two primary reflections. And of course that time interval is the time that it takes to travel two ways through that rock layer. And use of this characteristic of periodicity, as it's called, can be made in processing to try to eliminate these multiple reflections from the trace and leave just the primary reflections, which are the ones that we want to see. Now, another special class of multiples are the ones that are called reverberations. These are multiples which occur in the shallowest layer in the Earth. Now, generally they're most severe on marine seismic recordings, where that shallowest layer is the water layer. They're particularly severe because the reflection coefficients at the surface and at the water bottom are relatively quite high. The reflection coefficient at the surface for a ray incident from beneath the surface is approximately -1. That means that almost 100% of the energy is reflected back down from the water surface, and it undergoes a polarity reversal. The reflection coefficient at the water bottom is generally much higher than it would be between two different rock layers in the Earth, because there's quite a big difference in velocity and density between the water and the solid rock below the water bottom. Now, another characteristic of reverberations is that because they occur in the shallowest layer in the Earth, they give rise to a series of reverberation events following every primary reflection on the seismic trace. So that if we had a trace such as this with some primary reflections on it, there would be a sequence of reverberation events following each one of those primary reflections. If we look at just one of those primary reflections and the reverberations which follow it, we can see that the reverberations have a certain pattern to them. If we assume that the amplitude of the primary reflection is 1, or unity, just for simplicity, then the polarity of the reverberation events alternates in most situations. That would be where the reflection coefficient at the water bottom was positive. The amplitude of them is given here, and it's determined by the reflection coefficient R at the water bottom. So we have a sequence of reverberation events then of alternating polarity and gradually decreasing amplitude. Now, as with any other kind of multiple events, they have a constant time interval or periodicity, and that time is the time it takes to travel two ways through the water layer. Another type of event, reflection event, which always occurs on seismic records, although it's again more severe on marine records than on land records, is a type of event called a ghost. And ghost reflections are formed in this way. If we have the seismic energy source at some distance below the surface of the Earth or surface of the water, then a ray of energy which travels down into the Earth in this direction and eventually forms a reflection is not the only ray of seismic energy traveling in that direction. There is another ray which travels first of all up towards the surface and is reflected back down again to travel in the same direction as the first ray. So that if we were looking from some point way down in the Earth at the energy which arrives from this source, and let's assume again that the waveform of that energy is just a simple spike, we would in fact see two events arrive. We'd see first of all the primary event, that is the impulse which has traveled directly from the source, followed a short time later by a ghost event. And that would be the energy which has traveled to the surface and back down again. Of course, it's later by the amount of time that it takes to travel from the source to the surface and back to the depth of the source again. And it's normally reversed in polarity compared to the primary event, because the reflection coefficient at the surface is generally negative. And in the case of marine work where the surface layer is the water, that reflection coefficient is about -1. So in fact, if we have a source which generates a single sharp impulse, the waveform of the energy traveling down into the Earth is actually a double impulse of this type because of the ghost reflection. Now, ghosting can also occur at the receiver end of the travel path if the receiver is below the surface, and this is a situation in marine work where the receivers are below the surface of the water in the seismic streamer. On land, they're sitting on the surface, and so we don't get ghost reflections at the receiver end of the travel path on land data. But the situation would be this, that a reflection impulse arrives back at the receiver along a travel path like this, but also reflection energy arriving along a travel path like this is reflected back down from the surface and also picked up by the receiver. Now, if the reflected impulse is in fact a double one, like this, due to ghosting at the source end of the travel path, then this double impulse is recorded twice, obviously once by the direct path and once by the ghost path. There's also a polarity reversal again at the surface. So the type of reflection impulse that would be recorded would actually be a combination of 4 pulses such as this. The direct one, followed by the ghost from the source end of the travel path, and then followed by the 2 impulses which are due to ghosting at the receiver end of the travel path. Those would be reversed in polarity compared to the first pair. So in fact, in marine work, if we had a source which just generated a single impulse, the reflection events which we record would each of them be a combination of 4 pulses due to the ghosting at the source and receiver ends of the travel path. These ghost reflections can be relatively strong and have to be reduced or removed by processing of the data later on. Well, so far we've looked at the types of reflection events that arrive back at a receiver without too much consideration of the amplitude of those reflection events, other than to say that ideally they would be proportional to the reflection coefficients in the Earth. But in fact, there are a number of causes of amplitude loss as the seismic energy travels through the Earth. So that, in fact, the seismic trace we recorded at the receiver may look something like this. the amplitudes of the early reflections or multiples or ghosts or whatever would be very, very high, and the amplitudes would decrease rapidly down the trace until they were almost invisible. Previously we've been considering the seismic trace looking like this, where the amplitude of all the various reflection events were determined solely by the reflection coefficients. In fact, this is the type of trace we would like to see, but this is the kind of trace we actually record, and again, processing is used to convert the trace from this situation to this situation later on. However, the causes of amplitude loss on the recorded trace are several, and the main three that concern us are what are called spreading losses, absorption losses, and transmission losses, and we'll look at each of those in a little bit more detail. The spreading loss is simply due to the fact that seismic energy is traveling out in all directions from the source. So that if we looked at the wave fronts at 3 different times after the energy has left the source, it would look like this. And if we again imagine the shape of the seismic waveform was just a simple spike, then we would see the amplitude of that spike decreasing away from the source along any particular ray path. This is due to the fact that, of course, a certain amount of seismic energy leaves the source, but as the wave fronts increase in area as they travel further away, that same amount of seismic energy is distributed over a larger and larger surface, and therefore the amplitude of the waveform at any particular point on that surface along a ray path decreases, because the energy has been spread more thinly, so to speak, over the surface. In fact, it turns out that the amplitude of the seismic waveform is inversely proportional to the distance from the source. So we can determine this, the magnitude of this spreading loss, and correct for it in processing. Now, the second cause of amplitude loss is absorption, and this is simply due to friction between the vibrating earth particles as the wave travels through the earth. The particles move slightly in relation to each other, and the friction between them converts some of the seismic energy to heat, in fact a very minute quantity of heat. So this causes a decrease in amplitude of the seismic wave, and it turns out that it decreases by a constant factor each increment of travel time, each second, for example. And typically it decreases by about 10 to 20% per second of travel time due to absorption. The third type of amplitude loss is that due to transmission. Now, we showed that before that when a ray of energy is transmitted through an interface, the amplitude of the transmitted ray is determined in proportion to the amplitude of the incident ray by this formula. It's equal to the amplitude of the incident ray multiplied by 1 minus the reflection coefficient. Now, of course, any ray path has to travel 2 ways through the interface. This would be for a primary ray path, once going down and once as it travels back. Now, the reflection coefficient looking from the underside of a particular interface is simply minus the reflection coefficient on the upper side of the interface. So that in fact the amplitude of the transmitted ray traveling upwards is determined from the amplitude of the incident ray by this formula, 1 minus the reflection coefficient, which is minus RC in this case. So For the upward traveling ray, the appropriate formula is this, the amplitude of the incident ray multiplied by 1 plus RC. Well, in effect then, the amplitude of the ray is scaled by this factor as it travels down and by this factor as it travels up. So we have a kind of two-way scalar applied to the amplitude of the seismic wave. Call that two-way scalar T2, and it's simply multiplication of the scalar on the way down and the scalar on the way up. And that becomes this formula, 1 minus the reflection coefficient squared. If we take a numerical example of that, if the reflection coefficient was 0.1, which is a fairly strong reflection coefficient in practice, then the two-way scalar applied to the transmitted energy is 0.99. So that says that although the amplitude of the reflected ray is 10% of that of the incident ray, there is only a 1% amplitude loss of the ray due to transmission in two directions through that interface. So in fact, the amount of energy lost due to transmission is not as great as might at first be imagined. Well, so far we've assumed that the shape of the waveform traveling through the Earth was a simple spike. In fact, that is not the case. Even though sources such as dynamite give a fairly sharp impulse, it's not a single spike, it might be some little waveform such as this. Now, as that waveform travels through the Earth, it tends to increase in length. And if we look at a particular reflection travel path and look at the shape of the seismic waveform at several points along that path, we'd see that even though it starts out as a fairly short, sharp impulse, it gradually lengthens as it travels through the Earth, so that it may be in this state when it arrives back at the receiver. Now, when the signal is recorded at the receiver and is passed through the instruments to be recorded on tape, the instruments themselves, due to their filtering action, result in a further lengthening of the waveform, so that as it's recorded on tape, it may finally be a waveform of this length, even though it started out as a much shorter waveform at the source. So in other words, the reflections we obtain from each interface are not simple sharp impulses, they're waveforms, relatively long waveforms, more like this. So if we look at the effect of that on the seismic trace, then it means that where previously we've had a simple spike reflection or multiple reflection or whatever for each event, each of those spikes is now replaced by the appropriate waveform depending on its arrival time on the trace. The deeper events would be replaced by longer waveforms. So the trace as it's recorded actually ends up looking something like this. And of course it's much more difficult now to determine where we have an individual reflection event on that trace, because the waveforms, or wavelets as they're usually called, tend to overlap. Well, the trace with all the reflection events on it looks something like this then, as it would be recorded. One of the main things that is missing from the trace, though, so far is the various kinds of noise that are also recorded. Now, the noise, in effect, is added on to the reflection trace as we've just seen it. The noise can be subdivided into two main types of noise, random and non-random. Random noise is noise which has no particular relationship from trace to trace on the seismic recording. And it might be caused, for instance, by wind noise on the recording spread. Any wind would blow directly on the receivers sitting on the surface in land recording, or it may, the wind may cause movement of trees and bushes on the surface, which again causes very slight movements of the earth, and the very sensitive recording system picks up this movement of the earth, and it appears as noise on the seismic traces. In the case of marine data, the wave action on the surface generates a certain amount of noise which is picked up by the seismic receivers. Another cause of of noise on the seismic recordings is electronic noise generated by the recording instruments themselves, and this can sometimes become significant at later times on the record. The other main type of noise, non-random noise, is mostly noise which is generated by the seismic source itself. And for example, refraction events from the near-surface layers and direct arriving energy such as ground roll are forms of noise, in that they are events on the seismic record which are not reflections, and are also events which we don't want on the seismic recordings. These noise events, such as refractions and ground roll, are often sort of lumped together and called near-surface waves, since they all are due to modes of travel which take place in the layers of the earth near the surface. Well, just to look a little more closely at those near-surface noise modes, if we have a seismic source on the surface here and several receivers laid out on the surface, then of course we have direct travel paths for energy from the source straight along the surface or just below it to the receivers, and we also have refraction travel paths along some of the higher velocity layers just below the surface. So energy travels down to a higher velocity layer and then is refracted back up into the surface layer and picked up by the receivers. Now, if we look at the arrival times of these different forms of near-surface energy on a series of reflectors laid out on the surface, we'll see they form a certain pattern on those traces. The direct traveling P-wave energy, which is the fastest mode of travel, of course arrives first, at least on the nearer traces on the record, and it obviously takes about the same amount of time to travel between each of the reflectors if they're laid out at equal distances apart, as they usually are. So the P-wave energy then lies along some straight line across the set of traces. The ground roll energy, which also travels in a direct line, but at a much slower velocity, must always arrive later than the P-wave energy, and so it also lies along a straight line across these traces, but at later times and with a steeper dip because of its slower velocity. The refraction events on the near receivers, the refraction travel path may actually take longer than the direct travel path for the P-wave energy, but for the receivers further away from the source, the refraction path may actually be the quickest path because it travels at a higher velocity along this layer. So the refraction events again tend to lie in a straight line across the traces, but again with a different dip, so that they may arrive before the direct P-wave energy on the longer offset traces, but would generally arrive later than the P-wave energy on the near traces. So these are some of the forms of near-surface energy travel which result in what are called the near-surface noise modes on the seismic record. And again, those are types of events that we don't really want to see on the seismic data. We're only interested in the P-wave energy. So, summarizing then, we can look at what the final trace is like on our seismic recording. We had a series of reflection events of different types, and each of these reflection events is some waveform on the seismic trace. So in fact the trace with all the reflections on it, that would be the primaries, multiples, reverberations, etc., would look something like this. Now added on to that reflection trace we have the various kinds of noise. These would be the non-random noise modes, such as the near-surface noise waves, which form some particular pattern on the seismic traces, plus the random noise events such as wind noise and so on. So adding all those together, we would record a trace that maybe looks something like this, where it's very difficult and maybe almost impossible in many cases to distinguish the primary reflections on that particular trace. And of course it's only the primary reflections that we really are interested in. So we record a trace that looks like this, but in fact what we want is a trace that looks like this, which contains only the primary reflections. Each of those reflections is some very sharp waveform, preferably just a single impulse, and where the amplitude of those primary reflections are proportional to the reflection coefficients of the particular interfaces. So this, the problem that we're faced with in processing seismic data then is to transform the traces which look like this on the recordings into traces which look as much like this as possible. And the various ways in which that can be done by seismic processing will be looked at in subsequent lectures.